Okay. So I'm going to get started. Reminder, if you're taking this for credit, that there's a sign-up sheet somewhere out there to make sure I can record attendance. If you guys could remind me, if I start writing small, it's really bad for the camera. So if you see me writing small, just either shout out or raise your hand to write bigger. This is too small to see on the camera. So the first homework's out. It's up on the website. If you're taking this for credit, please submit it on Gradescope. It's due next Wednesday. If you have any questions, you should post them publicly on Piazza if possible, and it's reasonable to do so, because that way I can actually not have to answer the same question a bunch. The other thing is you should install, you can solve the problems on the homework using any Convex solver that you want, but the official support is for CVXPy and convex.jl. So if you ask me a question about other solvers, I won't necessarily be able to answer that for you. So it's highly recommended that you should install either CVXPy or convex.jl. Those are parsers. You'll also need a solver. So the ones I recommend are either downloading the splitting cone solver, SCS, or if you're going to be using this longer term, get yourself a MOSEC academic license. With an academic license, it's free. MOSEC is pretty great. Any questions before I start? Okay. So today's topic is, we'll see two motivating examples about why linear optimization just isn't going to cut it for us, why we need to be able to do slightly more general problems. I mean, I think that's pretty obvious to everyone here. And then we'll move on to, this is one of those lectures. There are two kind of theory lectures or basic lectures. This first one is on convex sets, functions, duality, convex sets, functions, being able to show that things are convex, etc. There will be next Thursday a lecture on duality. That one's going to be a little bit more theoretical, but these are kind of just unavoidable preliminaries that we need to cover. So first example I'm going to talk about today is we're going to design an index. So, I mean, I make a grad student salary, so I typically can't afford a full index fund or every single stock in an index. So let's say I'm trying to track the S&P 500. So we're given N stocks that we can buy. These are the ones we trust to do. So R is a random variable, and Rn, this is going to be the return of those stocks. Let's say that we've done our research well, so we know what the average return is. And we have a good idea about what the variance of these returns is. This just means that the matrix is positive semi-definite. If you don't know what that means, don't worry about it. Okay, so my objective is to be able to track the performance of this index by buying as few stocks as possible. So if I want the least number of stocks, so we'll just say that we'll let W is going to be our decision variable. This is going to be in Rn. And this is the number, weight given to each stock. So this is how much of each stock I'm going to buy. So what I'm trying to do is I want this W to have as many zeros in it as possible. So the basic idea behind that is it's going to be cheaper to buy fewer of the stocks, and it's going to be also much cheaper to rebalance the portfolio if I'm tracking a much less than the 500 in the S&P 500, right? So what is my objective function given everything I've said? I'm not trying to maximize the return because I don't think I can beat the market. I'm trying to design something that tracks this with the fewest number of stocks bought. So what I'm trying to do is I'm trying to minimize number WI more than 0. There's also card WI, card W. So now I said I want to track this return. Track performance with percentile. Okay, so I want to track the performance of this index within a certain tolerance. So I'm going to define this quantity, the error, or the percent error. It's the expectation So this is the relative mean square error. So if I want to track this within an error of t, I'm trying to solve this problem. So we'll talk about convexity and convex functions and things like that. Go ahead.
What is C?
Sorry. C is the current cost of each stock, or the index weights, rather. So how much in the S&P 500 is each stock actually weighed? So ignore the constraint for now. What do we think is bad about this objective right here?
I have a question. So C is like C and W are uniform with something one?
They could. It's not really important that they do. Sorry, can you repeat that? I can't hear you. The objective is minimize the cardinality of W, the number of non-zero entries in W. The problem with this objective is it's very non-smooth. It's not even differentiable. So a good heuristic for trying to encourage sparsity is to replace cardinality of W. This is also called the zero norm. We're going to replace that with the L1 norm. If you ever need sparsity in your problem, this is a very good heuristic for encouraging it. So now what did we say about the L1 norm last time? What kind of objective is it?
You can rewrite it to be linear.
Exactly. So I'm still going to have a linear cost. But, so we're going to be able to give a heuristic that has at least a linear cost. But what about this constraint? It's got squares, it's got square roots. Do we have any chance of making that linear? The answer is going to be no. But let's write this in a little bit smarter of a way so that we can at least write it so that it looks a little bit quadratic at least. Because quadratic functions, they'll turn out to be convex functions, which will be really nice. So what we want is for this quantity to be less than or equal to t. So the first thing I'm going to do is, since this is square, I can definitely move it to the other side without violating the inequality. Whenever you do that, make sure your denominator is non-zero, because otherwise you will mess things up. So, okay, now this expectation, I need to do something about it so that so I can write it in terms of the quantities I'm given. So the first thing I'm going to do is I'm going to write this square, C minus W transpose R. Anyone have a question about that? Okay, so this is, what I'm about to do is known as the trace trick. This is a very, very common trick that you'll use all the time, and that's why I'm bringing it up now. So what's the dimension of this quantity? Scalar, a vector of size 2, a vector of size n. It's a scalar. So what's the trace of a scalar? It's just itself. One of the properties about trace that turn out to be very nice is that the trace is what's called circularly symmetric. You can always shift these indices over by 1. Okay? So if I do that, I'm going to get C minus W. Chalk broke. Okay, now the only thing that's random in here is that R. Trace and expectation. Trace is linear, so I can pull it out. I can pull out the linear factors. Okay, now what's this quantity right here? Compare it to over here. This is the second moment. I gave you the variance, this is the second moment. So this is equal to C minus W transpose sigma plus R bar transpose C minus W. Subject to, this is the 2 norm. Transpose squared less than or equal to T. So now, this, we'll talk about whether that's going to be a convex constraint or not. And we'll talk about why that's important. But clearly, this is a problem. It's pretty reasonable. I want to design an index fund. I want to make sure tracking error, which is most of the time when we're talking about errors, we square them. That's clearly not a linear constraint, so it doesn't fit into the framework we talked about last time. Am I missing any constraints here? I'm talking about a portfolio optimization problem. So what does that mean about my weights? I want something realistic. My weights should be positive. I'm going to use these curly inequality things to denote component-wise positivity for vectors. But they should be positive. What would it mean if I had a negative weight? I can't hear you. Yes, it'd be a short position. It would be a short position. The reason I bring this up is optimization is both very smart and very dumb. It gives you exactly the thing you ask for. So if I ran this without this constraint, and I don't understand how short positions work, I'm going to be told to take short positions, which I might not want. So when you're debugging your algorithms or you're looking at the answer, first, make sure your answer makes sense. And if it doesn't, check that you've actually put in all the constraints you want. There's no such thing as an implicit constraint. It will give you exactly the thing that you ask for. All right. Next example I'm going to go over is arbitrage.
So, like, what was the main purpose of that transformation? What did we get?
We'll go back to that as to why you write it the way I did. When we talk about, we'll circle back to that at the end. I have to remember not to do that. Okay, so we're about a month and a half away from the Super Bowl, and so some people like to bet on sports games. So let's say, so we're going to consider N, I'll call them assets, with prices P1 to Pn. Okay? So these are going to be the prices at the beginning of the investment period. So these are going to be the prices that different booking agencies have for laying down a bet. Now, after the game, if I'm doing something like soccer, this is more likely. But after the game, there's really only a finite number of reasonable scores that could happen. So after the game, all of these bets can have the following set of values for what they'll actually be, what the actual value of the bet I placed is. So that I don't forget, the attendance survey code for those of you who are remote today is sports betting. Okay. So let's think about a set of initial investments, x1 to xn. So what an arbitrage is I'm asking the question, is there a way I can buy this set of initial positions so that no matter what the outcome of the game is, I'm going to make money? So mathematically, what that means is, does there exist an x such that P transpose x is less than 0, V transpose x is more than 0. I'm centering this around 0 by basically because I can actually just shift it up and down arbitrarily. This basically means I'm paid to accept a certain betting position. No matter what I do, can I be sure that I'll make money? So, do I have an optimization problem from this? Yep.
Just to clarify, P transpose X is a scalar, right? And V transpose X is a vector?
Yes. Component-wise more than 0. Because if it's component-wise more than 0, no matter what the outcome is, I made money. Do I have an optimization problem? I do. Okay. I do have an optimization problem. These are the constraints. What's my objective? There isn't one. It's just find x. So I may as well write this as min 0 transpose x, right? So what kind of problem do I have right now? An LP. Yep. So this is a linear program. But here's what's going to happen if I realize I have an arbitrage opportunity. If I have an arbitrage opportunity, I'm going to take all of my savings and dump them into the sports betting arena because I know I'm going to make money. So I may as well do that. The thing is, as soon as I realize there's an arbitrage, everyone else is also going to realize there's an arbitrage, and the prices are going to move by the time I finish putting in my bets. I should leave that. And I should leave this. So really what's going to happen is, well, they're going to move some, but I might have some idea about how they're going to move. So let's say that, let's say that for one of these columns in V, let's suppose that these are actually going to be random variables. But I know that they're going to lie in some ellipse oh, sorry. One. Right? So basically what this is saying is I have some point in space that's going to be my vertex, but I know it's going to be somewhere in that ball. Sorry, can you repeat that?
So like I'm looking at the program for sports betting, and the first constraint is that like the map would be made for the assets and the bot is not really.
Yeah, so what that's saying is I'm basically being paid to take up a position. I can't hear anything. So the reason that I want this constraint is I'm looking for a situation where I'm being paid to take a position. So really, I'd have to pay money, right? But I want there to be some positive return for being paid to accept a position. So when you can offset both of these by a constant and it doesn't matter. And that constant is going to be how much you actually put into the system. Right? Because it depends on what the current prices are, whether there's an arbitrage. Okay, so I don't just want, so this constraint, I'm just going to think about it for just one of them. Minus vi transpose x needs to be less than or equal to 0. Right? But I need this to hold for all the possible vi's that could show up as I'm putting down my bets. I want there to be sure that there's an arbitrage no matter what happens. So what do I need? I need that the supremum of vi transpose x such that vi is in my ellipse. I'm going to check that they still have sound. Hello? Yep. Okay. Okay. So I want to check that this is less than or equal to 0. Okay. So that's being that EI. Right? So the constraint I actually need, if I just multiply this potential thing out, what this VI transpose is going to be is it's going to be, I want soup. Okay, VI bar transpose X plus U transpose PI X. So finally, when I evaluate the supremum, realizing this final evaluation of the supremum is going to give me the constraint that okay. So this problem is called right here. This one plus I want it to be hold for some ellipsoidal uncertainty. This is called robust linear programming. Robust linear programming in this case is not a linear program, actually, right? Because this is, once again, not a linear constraint. Go ahead. No, P is some fixed matrix defining the ellipsis. It's defining the major and minor axes of the ellipses. Okay, so clearly we need something more than linearity, but we can't do arbitrary things. So that's where convex optimization is going to come in. So before I can talk about convex optimization, if you don't know what a convex function is and a convex set is, right now you are very confused, and hopefully I'm going to fix that. I'm going to go through this very quickly. So I'm missing a sheet. I'm missing a sheet. Oh, I'm missing one of the sheets, so we're going to do this out of my head. All right. So the first thing that we're going to talk about are convex sets. Okay, so set S is convex if for x1, x2, both in S, lambda in 0, 1. Lambda x1 plus 1 minus lambda x2 is also in S. So this is the definition, and it's very useful for, I mean, obviously it's useful for actually doing things. Oh, there it is. But what does it actually mean pictorially? So what it means pictorially is that if you give me any 2 points in this set, I can draw a line between them, and that line is going to stay inside the set, no matter what I do. So your classic example is going to be something like this. If I take 2 points here and draw a straight line between them, I don't stay in the set on that whole line. So that's the definition. There are a bunch of kind of key terms. You'll hear people talk about convex combinations of points. X is a convex combination of these xk's as long as these lambda k's sum up to 1. So that means I'm taking a bunch of steps and meeting in the middle. So there's also this notion of extreme points. So a point x is extreme if x So a point is extreme if the only way you can write it down is basically as a convex combination of itself. What this corresponds to in things like polyhedra are these corners. Right? So this whole face is not extreme because I can write any point on this line as a convex combination of the corners. But these corners are extreme because there's no way I can get to those corners without just starting there. What are the extreme points of a circle?
Every point?
Hmm?
Every point?
Extreme points of a disk. Just the boundary, right?
Oh, yeah.
Yeah. You're right. A circle is only the boundary of the disk. Okay, so a sometimes useful fact, depending on what you're doing, is a compact convex set convex So a compact convex set, basically meaning a closed and bounded set, this doesn't really apply for things that are open, is a convex combination of all of it. It's the convex hull of all of its extreme points. I know this feels like a laundry list of definitions, but these are very common vocabulary words that you need in order to be able to actually talk about a lot of these things. So what is a convex hull? There are a bunch of equivalent definitions for it. One is this, so conv S is equal to the set lambda x plus 1 minus lambda y, lambda in 0, 1. So the convex hull of a set is just, you take every point in that set, you take all the possible convex combinations you can take with every other point in that set, and that's the convex hull. So if a convex set is the convex hull of its extreme points, what does that mean the convex hull of the set is? So if S is convex, then the convex hull of S is S itself. For a set like this, if I take 2 points, draw a line through them, well, the convex hull has to now include this line, has to include every line here. So the convex hull is actually going to be this whole thing. So intuitively, what a convex hull is, and this turns out to actually be true, is it's the smallest convex set containing S. This turns out to also be equivalent to the intersection of all convex sets T such that S is a subset of T. So those are 3 kind of equivalent definitions of what the convex hull of a bunch of sets is. But it's basically the smallest outer convex approximation of the set. Are there any questions so far? Yep.
Yeah, so this definition, so a convex set, you basically say that like for a set of points we can define the convex set as the convex hull of the extreme points of that set.
Mm-hmm.
What's the compact part? Where does that come into difference?
Compact means closed and bounded. So like, I mean, a cone is a great example, right? This is open because it's going off to infinity. So you need the compactness thing so that, like, the convex hull of, in this case, this is fine. But like, you could have a convex set that is the open disk, right? Well, what are the extreme points of the open disk? There aren't any, right? I can just approach the boundary and never actually get to something. That's still a convex set, because any 2 points I can draw a line between them and stay inside.
So that's a convex set that's not compact.
Yeah, exactly. The cone that I drew was actually. So the last 2 kind of notions is the idea of a cone. So cone is if theta 1, theta 2 more than or equal to 0, x1, x2 in S. So cone if x equals theta 1 x1 plus 2 x2. So that's the definition of a cone. Are cones convex? The answer is yes, right? Because if I make this lambda and this 1 minus lambda, and lambda is between 0 and 1, this is positive, so it's be convex, right? A conic combination, based off the definition of convex hole, is exactly what you'd expect. It's just the sum of a bunch of points where all of the coefficients are more than 0. Okay, so there are three basic convex sets that you should just be aware of, and these are the most important ones. So the first one is the half space, right? So what does the half space look like? Just looks like that. I'm just cutting whatever dimension I'm in and have that. The next one are norm balls. This is the set x such that x less than or equal to r. This one, so I mean, the one people are most familiar with, and you can offset these, but the one people are most familiar with, the L2 ball. Another common one is the L1 ball. So any norm is a convex function, we'll see, but any set defined by a less than or equal to sign norm is called a norm ball. It is also convex. And the last one is the norm cone. And so that's the set xt such that. And so the most common example of that is just the Lorentz cone. Okay. Yeah, I erased the wrong board. That's okay. Okay. So, operations that preserve convexity. Again, I'm not going to prove any of these, but these are good things to know that they exist. Because the way that you most often prove that things are convex is by showing that they're the image of one of these things. So the first one is intersection. So the intersection of convex sets is always convex. The intersection of closed sets is closed. Intersection is something that usually preserves properties. So the other really common one is you show if you take a convex set S, so for example that ball, and you pass it through a linear function, the result is going to be convex. Equivalently, or not equivalently, but also a fact, is if you have a linear function, you take a convex set, and you pass it through the inverse of that linear function, you also still have a convex set. So it's image and pre-image. This last one you'll use slightly less often, but it's useful to know. This is called the perspective. So if you pass a set through this function, or so it's image and pre-image. Both of these operations also preserve the convexity of your set, both image and pre-image. Go ahead.
Wondering how the mathematical definition of the norm cone gives us a cone. Is t like another coordinate?
Yes, t is another coordinate. So the way these differ, right, is this is a constant, which creates a ball. This is a, this is a norm cone. So this gets to float around too.
So the points are x and t taken together?
Yeah, exactly. Cool. Okay. Moving on to convex functions. I think I spent too much time on the examples today, so I'm going to have to move quick. Okay. Convex sets, cool. Okay. So, f is a convex function if, okay, first the domain of x is convex. Second, I need this condition to be true. So what this corresponds to is that if I evaluate the function at two different points, if I take the convex combination of those evaluation points, I need to end up less than that value. So most common examples of these are affine functions, the exponential, powers of functions if x is more than 0. Absolute value is the absolute value raised to a power is always going to be that, and all norms. And when I say all norms, I actually mean all norms. So if you think about the maximum singular value of a matrix, of a positive semi-definite matrix, that's a norm on positive semi-definite matrices. So the function that asks for the maximum singular value, or the maximum eigenvalue, is a convex function because it's a norm. If you want to prove that directly, be my guest. Okay, so there are a couple of equivalent conditions. I'm going to do, okay, so if f is these obviously only hold with differentiable f, and this first condition always has to be satisfied. But other ways of satisfying this is so the first one is what's called the uniform under approximator condition. Basically says if I take the tangent line at any point, I always under approximate the function. I'll meet it here. I'll meet it at the point I'm taking, but this line is always going to be an under approximator for the function. The other one is that the Hessian has to be positive semi-definite for all x if you can get a Hessian. And the last equivalent way of defining convexity that I'm going to talk about is, okay, so I'm going to define this epigraph of the function f. This is equal to the set xt. X has to be in f of x. Sorry, in domain of f. And then f of x has to be less than or equal to t. Okay, so f is a convex function if and only if its epigraph is a convex set. So what is the epigraph of the set? Basically take the function right here and you fill in the space above it. That's the epigraph of the set. And so if a function is convex, that means I can draw a line, and this whole set is also going to be convex always. Maybe I can do this here. Questions? Okay, so these are the ones that preserve convexity of functions. By the way, this condition what this condition is actually telling you is that the set of x, if f is a convex function, the set of x which satisfy this inequality, that's a convex set. We'll come back to that when I tell you what a convex optimization problem is. Okay, so operations that preserve convexity. non-neg weighted sum. That function is going to be convex. So if f is convex, then g of x is also going to be convex. This is called composition with an affine function. G of x is the pointwise maximum of a set of functions, is going to be convex. Coordinate-wise minimization is a convex function. Again, the assumption here is always that the f is convex. This last one is called perspective. Sorry, strictly. Okay, and this last condition kind of subsumes all the other conditions. This is a bad eraser. So this is actually the one you want to remember the most. Okay. So g of x is equal to f h of x. So g is convex if, okay, so 1, f convex, h convex. I'll tell you what h tilde is in a second. Okay. I think that order right, yeah. H tilde to h. Okay, so h tilde is what's called the extension of h. So basically what you want is that, so if h looks like this, it's increasing, right? And I also want to be sure that I jump to infinity correctly in this, with those two conditions. Those are kind of technical ones. You don't have to remember them too much, but they are important for completion, for them being complete. All right, so I have 20 minutes. Okay, so what is a convex up? I know what I wanted to do. Go ahead. Oh. Thank you. Domain of H. Because I switched things from how I wrote them down in the notes. Cool. Okay, so based off of these rules and everything I've told you so far, why is this function a convex function of x? Is a linear function convex or concave? It's both, right? Concave, by the way, means that minus the function is convex. Okay, is this convex? Why? It's a norm, perfect. Well, this is a norm, but what am I doing to it first? I'm composing a convex function or norm with an affine function, so that preserves convexity, and that preserves convexity, so yes. What about here? The decision variable is w. So this is constant, don't need to worry about it. That's why, to answer the question earlier, I wrote it this way. It's because otherwise, I've got some like weird scaling happening, but it's not that important. So again, composition of a norm with an affine function. So I'm convex. So now we covered that. What is a convex optimization problem? This is the definition of a convex optimization problem. Ignoring the, so does this encompass all, are these two things equivalent? Can every problem like this be written like this? The answer is no, right? Because what I could do is S could be the intersection of two non-convex sets. This is slightly stronger. I'm requiring each individual set to itself be convex. Okay. So one of the natural questions is, so a convex function is pretty nice because it basically looks like a bowl, right? So it's gonna, all the local optima are going to be global optima, okay? So the thing that's nice, so that's why the objective is good, because I can just march until I feel kind of optimal, meet some optimality conditions, and I know I'm globally optimal. The intuition I want you to have about why these are the right sets of constraints, or the types of constraints I can handle easily, is the basic idea about the basic geometry of that's not convex, of a set of convex inequalities like this, is it basically says I can take if I'm at some point, if I take a straight line set, a straight line step, and I'm still inside the set, then I never actually violated my constraints. So that basically means I'm free to walk around in the middle of this set until I hit a boundary and just keep taking random walks and know that I'm never actually going to violate my constraints along the way. That's important from the algorithmic perspective, and that's why these are kind of problems that we can do good things with. walking along discrete lattices, I have to take very fixed, there are only certain types of steps I can take. And that's what kind of makes the algorithms for those problems a little bit harder to actually implement, because you can't just take these arbitrary steps to keep improving. The reason that you want to stay on affine equalities is actually for the same reason. If I draw a line in this set, again, these algorithms update by taking linear steps. I never take these curved steps in between. So by having an affine equality constraint, I can take linear steps and always, stay on the feasible set the whole time. So that's kind of the intuition behind the geometry of those rules from the algorithmic perspective. Okay, so how do convex optimization solvers actually work in code? Oh, you know what? I'll get to this point in 1 second. Okay, so I said that there was something that was special about convexity. The things I said that were special about convexity were the uniqueness of that solution. I can basically walk around and be fine. Where's that last page? Okay, here's something that's not. Here's why convexity is. A lot of people are fond of saying convexity is kind of the end of the story. Once you're convex, you're fine. It's actually not quite true. If anyone ever tells that to you, you can tell them that they're wrong. So if L of x is a linear function, it is provably true that these two optimization problems, even if omega here is not a convex set, these two optimization problems have the same optimal cost. Okay? So that means that an optimization problem like this even if f of x is not a convex function and omega of x is not a convex set, I'm realizing that people won't be able to read this. So again, f of x, imagine it's not a convex function. Omega of is not a convex set. These two optimization problems actually have the same optimal value. So why can't I just write everything like this? So this is actually like a very deep and difficult question, but it basically boils down to, sure, I can write this, but I have no way to represent this convex hull in a computer easily. There's no way for me to write that down in a simple manner that'll actually get me the solution. So convexity is not the end of the story. It's about convexity and being able to represent that. And so what most convex optimization solvers actually are what are called conic solvers. We'll talk about problem types starting next week, but most people when they talk about convex optimization are actually usually talking about conic optimization, linear programs, quadratic programs, semi-definite, etc. And so how do these solvers actually work? Like we talked about in linear programming, most optimization problems that have solvers implemented for them have a standard form. So for the simplex method, it was C transpose X subject to A of X is equal to B. The thing is, the transformation of those standard forms is kind of an algorithmic process. So when you're actually solving this stuff on a computer, what you normally do, so there are kind of 3 layers. There's the actual programming language that you're using, Python or Julia. Then there's this layer called the parser. The parser is the actual piece of software that lets you write x is less than or equal to 1. The norm of x plus 2 is less than or equal to whatever. And it lets you write all kinds of convex constraints that it then parses to translate into the standard form of the actual solver. That parsing step also sometimes involves some pre-processing steps. But this parsing can actually take can sometimes take longer than the actual solution times. So as you advance in this, if you care, sometimes it's worth digging into how the different parsers are translating to different standard forms and different solvers. So for example, CVX.Py and Convex.Julia, those are parsers. MOSEC, SCS, the things I mentioned earlier, those are the actual solvers that will give you your answers. So what's important for these solvers to be able to be sure that they're giving you the right answer, I need this, is they want to be sure that you have a convex problem. Because if you don't, they don't want to give you the wrong answer and think that it's right. Or they don't want to try to do something that they're not capable of doing. So that's one of the parser's jobs. In the case of CVX.Py, and basically the whole CVX library, there's this thing called the disciplined convex. It's called disciplined convex programming. It's an automatic way for them to check whether what you're giving them is actually going to be a convex optimization function problem. So if you will most likely need to Google this and look this up as a reference, but DCP, disciplined convex programming, that's the keyword you want to look at. DCP, a program that satisfies the DCP conditions, is convex. The converse is not true. You can be convex but not be DCP. But the basic rules here are that expressions have signs. So the expression x plus 1, sorry, let's do this. X squared has a positive sign. Minus x squared has a negative sign. X plus 1 has an unknown sign. So I can be positive, negative, or unknown. It does not accept both. And you don't actually have to specify that. It's just this is, when you declare x, it's going to be unknown. Or DCP, both of these libraries let you say x is going to be positive or x is going to be negative. It doesn't know whether it's positive or negative because it could be both, right? If x starts with unknown sign, x plus 1 could be positive or negative. If I forced x to say x is going to be positive, x plus 1 would actually have a positive sign. Okay, and then we also have curvature. So I can either be affine. So x has affine curvature. Constant. So f of x can be independent of x. I can be convex, which means that It's just the definition of convex. It can also be concave, or I can be unknown. And the basic rule underlying all of DCP analysis is it builds up this tree. So if no matter how complicated the expression is, I have to start from some basic primitives. And it essentially applies this rule up here to check whether I can prove that I'm convex, that I'm giving it a convex expression, right? So f x bar 1 to x bar n convex if f is convex for all x bar I, one of the following holds. F is increasing in arg I, and x bar I concave. Is that right? Should be convex. No, this is concave, convex. And then there's an equivalent formulation for concave. So minimizing a convex objective, good. Maximizing a concave objective, also good. Because maximizing a concave objective is the same thing as minimizing the negative of that objective. So that's why they let you have concave things, because you can call max on some of these. This rule is essentially that rule applied over and over again. So technically out of time, I want to show a very quick example, if you'll give me 5 more minutes, to show you how you have to be careful with the DCP rule set. So the example I wanted to, this is kind of a warning example. Let's say I'm trying to do this constraint. The vector 1 in x is less than or equal to 1. 2 norm, sorry. So we have CVX has a built-in function for this called norm2. It'll be DCP, it's fine. Let's pretend it didn't and you wanted to implement it. Okay? So what is the 2 norm? The 2 norm is 1 plus x squared. Okay? Let's say x I'm letting be the entire, x is just an r. Okay, so according to the DCP rule set, let's build this function up from its components. Okay, so first off, x is affine, right? So that means I can square it. And so the square is a convex function. The thing I'm putting into it is affine, so x squared is going to be convex. Now, I'm doing an affine transformation on it, right? So 1 plus x squared, still convex. Good? Okay, what does the square root function look like? Is it convex, concave, or linear? Or affine, sorry. That's what it looks like, right? It's concave. So it's concave and going in what direction? No, it's increasing. Yeah. So, okay, 1 plus x squared is, so f is concave. Of course, I didn't write that. So since f is concave, I need it to be, oh, right. So f isn't concave, but we know the norm is convex. So we know this is actually a convex function. But I'm about to shove something into it that's going to violate my DCP rules. So CVX is just going to say, yeah, I can't certify that's DCP. I don't think that's going to be a convex function. So that's why you have to be careful with these DCP rules. If you get the error, not DCP, not DCP, make sure that you're using as many of the built-in functions as possible, because otherwise you have to deal with this, okay, I need to tell them that this is positive. Because by the way, it's, this one I would say is positive, but these are kind of like the pitfalls. And so one of the problems on the homework assignment is actually going through these DCP things, making sure that they're DCP, changing expressions if they're not, etc.
So the point of this is that like DCP is not fully expressive in capturing everything, so they have to like hard code that the norm 2 is convex in whatever checker you use.
Yeah, so when you actually want to introduce a new function into the DCP library, into it, if you naively build it up from components, sometimes you can get DCP errors even though you're convex. So you do have to, it's rare, but you do have to sometimes implement the function and tell CVXPy that, yes, this is fine, this is a convex function. Typically, you won't do that, and the reason for it is because if you write your own function, the parser isn't going to be able to then translate it into a standard form for some of the solvers. All right, that's everything I have. Thank you guys for coming. Sorry I went a little over.